What is a tree data structure? Tree data structure is basically a non-linear hierarchical way to organize data using connected nodes, starting from a single root node, branching down to child nodes, and ending in leaf nodes, that is, with no children, resembling an upside down tree, ideal for representing relationships and efficient searching in systems like file directory or databases. Unlike linear structure, a single node can have many children forming branches. So, a tree data structure is a non-linear. Now, who all have watched Loki? Within Loki, there is a sacred timeline concept, right? The sacred timeline concept is a singular branch of time. And due to Nexus event, it causes to have multiple universes. So, when there are n number of Nexus events, it causes for a sacred timeline to have n number of multiverses. This condition is turning from linear to non-linear. And hierarchical. I hope you have played games. Hierarchical basically means level 1, level 2, level 3. So, basically hierarchy, levels. Within a game, it all starts with a tutorial level, level 0, then you go to level 1, then you go to level 2, level 3, and you level up, right? So that is hierarchical. So a tree data structure is a non-linear hierarchical way to organize data using connected nodes. Now, what are nodes? Nodes are basically entities, singular entities holding data. So, what did I say? Nodes are singular entities holding data, and the data within the node is called key. And it all starts with a single root node, like how our universe started with Big Bang, and branching down to child nodes and ending with leaf nodes. This relationship can be very well understood using a upside down tree. Now let's draw a tree. I hope you all have seen trees, right? So trees have roots, have trunk, has main branch, then secondary branch, then tertiary branch, and at the end leaves. Okay? So the trunk and the root part of a tree is root node. The main branch is the level 1 child. The secondary branch is level 2 child nodes. The tertiary branch is level 3 child nodes. And it all ends with leaf, which does not have further continuation. That is, no more children nodes. Level 0, level 1, level 2, level 3, level 4. Root node, level 1, level 2, level 3, leaf node. Okay? So, what are the uses of tree data structure? Tree data structure are ideal for representing relationships and efficient searching in systems like file directories and databases. And unlike linear structures, which has one-to-one relationship, a single node within a tree data structure can have one-to-many relationship. And depending on that, a tree data structure can be categorized into two parts, that is binary tree data structure and non-binary tree data structure. Now let's understand this concept with the help of a diagram. This diagram has been taken from the website called Geeks for Geeks, so shout out to them. So let's observe the diagram of the tree data structure. Here you can observe the first part, the first weird part, I would say. You are observing the levels, right? There is level 0, level 1, level 2, level 3, level 4. So Level 0 is the tutorial. As I was explaining in the hierarchical part, right? Level 0 is the beginning or the tutorial. Then there is level 1, there is level 2, level 3, and so on till you reach the last level, that is the epilogue. So prologue to epilogue, right? Now the next thing you will notice is the root node. As I previously mentioned, root node, which is containing data A, and that data is called key. Now the next thing you will notice is that two nodes are connected using something called edge. Edge are basically linking points between two nodes. Then there you will notice that there is a weird triangular structure. This triangular structure is subtree. Subtree, in the most simple word, is a smaller tree within a larger tree. As you sometimes might have noticed that there are trees growing upon trees, right? It is a very rare case, but many of us have noticed that. So it is something like that. Then there is the parent-child relationship. Basically, parent and child relationship is a relationship of two levels, with the upper level being the parent and the lower level being the child. And two child nodes sharing a single parent node are called sibling nodes. Okay? Then you will notice leaf nodes. Leaf nodes is the epilogue I talked about, the final chapter of our game. Leaf nodes are basically nodes which does not have further continuation, that is, no more child node. Here K, L, M, N, O, P and G are leaf nodes. So basically you can imagine it something like a multi-root game, right? Depending on your choices, you meet certain ends. So there are multiple leaf nodes here. And then you will notice height of the tree. Height of the tree is basically the distance between the furthest node. Here, except for G, K, L, M, N, O and P are furthest. So let's choose one, K. So the distance between the furthest leaf node and the root node is height of the tree. And we have to count the direct edges. Here 1, 2, 3, 4. So the height of this tree data structure is 4. Okay. Now let's move on. If someone asked me what is the best real life example for a tree data structure, now many of the lectures you might have seen will tell you it is a family tree. But I beg to differ. Family tree at the initial part contains at least 2 initial nodes, which is not a good example. Yeah, it might be a good example to understand or to visualize, but not a perfect example. Perfect example would be evolution tree. Shout out to biology students. Yeah, evolution tree. We all started from a single cellular being, right? And then evolved to what we are right now. So yeah, now let's understand or let's know the definitions, the official definitions. I have basically cleared all the things that are there in tree data structure in the raw part. Now let's read some official definitions. Now what is node? Node is a unit holding data connected to other nodes by edges. Basically a single unit holding a data connected by edges. Now what are edges? Edges are the link connecting two nodes. Then come root node. Root node is the topmost node with no parent or incoming edge and only children node or outgoing edge. Basically, what do I mean by incoming edge and outgoing edge? Suppose this is a random node. If it has a parent, there is an edge coming from parent to child, right? So this is incoming edge or the connection between parent and child. And if this particular node has children, then there is an outgoing node. That is that it has a child node. That's what I meant. Now, from the beginning I'm doing parent child, I have already explained it once. Let's do the official definition. So since beginning I am saying parent child. What is this parent child relationship within a tree data structure? Basically, the node directly above another is its parent and the one below is the child. Basically, a relationship between two levels, with the upper level being parent and the lower level being child, as I said. Then comes the leaf node, a node with no children, that is outgoing edges, and only parent nodes, that is incoming edges. The epilogue of our story, that is the ending of our story with no more continuation, is the leaf node. Then comes branch node. Branch node is basically something like this, something in the middle, which both have a parent node and a child node. A node which both have a parent node, incoming edge, and child node, outgoing edge. Then there is sibling nodes. As we covered, nodes which share the same parent node are sibling nodes. And finally, there is subtree. Subtree is a node not including the root and all its descendant. Basically, a smaller tree held within a larger tree. Basically, excluding the root node, we will consider another node, suppose C. So C and all its descendant, that are G, F, J, O and P, constitutes a subtree within a greater tree. Okay. Now let's clean up this diagram. It has become a mess. I hope that has cleared all your doubts regarding this tree data structure. Now, let's move on to some common uses of tree data structure. Tree data structure are used within file systems, databases, HTML, XML DOM, compilers, and AI decision making. Within file systems, it is used for representing folders and files. Within databases, tree data structures are used for indexing data for fast lookups. Within HTML and XML DOM, it is used for structuring web page elements. Within compiler, it is used for representing code structure like abstract syntax trees. Within AI decision making, there is a very famous term called decision trees. Within that, tree data structure has a role in it. Finally, some formulas for a tree data structure. Size of a tree data structure is equal to number of node. Let me explain. For this particular tree data structure, the size of the tree data structure is 1, 2, you will count, it will come up to 16. The size of this tree data structure is 16. Then there is the depth of a node. Depth of a node basically means the location of the sibling level down from the root node, considering the root node as level 0. Let's understand. The depth of root node is level 0. Depth of node B is level 1. Depth of node H is level 3. Depth of node K is level 4. So does that mean the node H, I and J share the same level or same depth of node? Yes. And finally, there is the height of the tree data structure. As I said, the number of direct upward edges above the furthest leaf node from the root. Basically, we have to choose the furthest leaf node, that is the K and root node, and we have to calculate the distance between them by counting the direct edges. Direct edges would be these, and hence the height of this tree data structure is 4. Thank you.